All right, let's look at discussion question number 10. All right, so we have two predator-prey models, systems of equations. One of these represents a system where the prey and predator are, you know, very different sizes. So where the predator animals are very small and the prey animals are very large. So like mosquitoes and elephants. Um, the other system are where the prey and predators are more comparable in size, such as foxes and rabbits. So how is that difference going to show itself in our differential equations? Well, if the predators are very small, it's going to take many of them um, to kill a single prey animal. So I think we should focus on these interaction terms. So, and a couple things, I'll not circle them because I don't want to obscure anything. So a couple things to look at with the interaction terms, the ones that contain both X and Y. Um, one in the equation that defines the death of the prey, you're going to need a lot of the predators to kill one prey. So because of that, I would expect the constant that's multiplied by xy to be very small. Looking at it another way, since the predators are so small and the animal they want to eat is very large, it's going to give them a humongous benefit if they kill one prey. So I would expect on the equation that defines or that describes the growth rate of the predators, I would expect that benefit, that coefficient to be very large. So because of that, I believe that system one, I believe X is, these are the prey, so these are elephants. No. These are elephants. Because I think it's going to take many mosquitoes to eventually kill an elephant. And DYDT, those are mosquitoes. On the other hand, how many foxes does it take to kill a rabbit? Usually just one. And in fact, one fox can probably kill many rabbits, and that often is the case. So because of that, DXDT, these are rabbits. In these, predator-prey models, the fact that these constants are negative. So since the interactions between predator and prey are causing a decrease in this population, the X's in either system are the prey. And since the interaction causes a benefit to the Y species, those have to be the predators. Basically, they're eating, they're getting nourished, which helps them survive and procreate. So finally, these are the foxes here. So hopefully that makes sense on how I'm identifying each one. All right, so part one is done. Part two, identify all the equations of Null-Kleins and equilibrium points for each system. Okay, so for system one, basically, how do I find Null-Kleins? I want to set each one of these equations equal to 0. So this first equation, if I set this equal to 0, if I look at this as, I can look at this as I have two terms. One of them is 10x times the quantity 1 minus x over 10. The other is 20xy. Both of those have an x in common. So let's do this. dx dt equals x times 10 times 1 minus x over 10 minus 20y. And that equals 0. So I have one very simple factor times one much more complicated factor equals 0. So that gives me one equilibrium or one null climb value x equals 0. That was pretty trivial. If there's no prey in this system, then the predators will also go extinct. Or I mean, it's equilibrium because if x is 0, then dx dt will never change. There's no way for them to reproduce. The other equation can I solve for y? So let's expand. So 10 minus x essentially minus 20y equals 0. Negative 20y equals x minus 10. Y equals negative 1 over 20x plus a half. So these are my null climbs for equation 1 or dx dt from system 1. Similarly with the foxes, two terms, I have y in common. So factor that out, and then I have negative 5 plus x over 20 equals 0. So again, I have this trivial case where y equals 0. So if the predators are extinct, then they will not, that will never change. The other condition I have is that x over 20 is equal to 5, or x equals 100. So those are my null climbs. If I have 100, if I have 100 rabbits, that will result in a in the rate of change of the foxes being 0. Okay, so now where do I have equilibrium? So for system 1, equilibrium is going to happen anywhere where a rabbit null climb intersects a fox null climb. So let's start with one of the rabbit null climbs, x equals 0. So 0, 0, basically that's extinction. That's an equilibrium, but probably not a very interesting one to think about. Can x equal 0 cross the other null climb? No, x equals 0 and x equal 100 are parallel. So that can't happen. All right, so now let's look at the other rabbit null climb. Y equals negative 1 over 20x plus a half. Will that cross y equals 0? I think it will. So let's plug in 0 for y and see what I get. Let me go ahead and move my thumbnail here. So 0 equals negative 1 over 20x plus a half, which means that x over 20 equals 1 over 2. Cross multiplying gives me 2x equals 20, so x equals 10. So it looks like I always also have equilibrium at 10 rabbits, no foxes. So that's like, does that make sense? Should I have expected to find equilibrium at 10 foxes or 10 rabbits? Hopefully, because that's kind of what the carrying capacity of this is a logistic growth model here. And if there are no foxes, then this term is gone. So this essentially becomes just logistic growth. And if we're at the carrying capacity, we have equilibrium. Last thing to check out. Can this null climb intersect with x equal 100? I think it can. So let's take a look at that. So y equals negative 1 over 20 times 100 plus a half. I actually don't think that it crosses in any kind of meaningful way, or what does it? It has to be negative 5 plus a half. So that's a negative amount of foxes, so I don't think that makes sense. So these are my equilibrium. The only equilibria I have for this system is where both cases are where the foxes are gone. And just to make sure, can I have intersections between the other cases? Just want to be totally sure. I'm just double checking my equation that I got, the y equals -1/20x. So I factor out the x, I get x times 10 times 1 minus 10 minus 20y, 10 minus x minus 20y. X equals -1/20, or y equals -20. Okay. Okay, I feel good about those two equilibria. Now let's do the same thing with elephants and mosquitoes. For the first equation, dx dt, factor out the x, and I get 0.3 minus y over 100 equals 0. So that gives me what? X equals 0. And y over 100 equals 0.3. That equals 30. So two null lines. X equals 0. Y equals 30. So those are both my x null lines for this system. In the second equation, I can factor out a y. If I factor out a y, what's left is 15 times 1 minus y over 15 plus 25x. So here I get the, elephant extinction case. So where y equals 0, I'll have a null line, but what else will I have? The other case is 15 minus y plus 25x equals 0, which gives me what null line? Y equals 25x plus 15. All right, so I got my two null lines for each. Two of them are relatively trivial. So now where am I going to have equilibrium here? So we can do the same kind of checking intersections between each one. Let's say x equals 0. Is it possible for x equals 0 and y to equal 0? Yes, that's true. So one of my equilibrium here is, again, extinction. No elephants, no mosquitoes. What about x equals 0? Can it cross y equals 25x plus 15? I believe it can. In that case, my equilibrium will be, well, if I plug in 0 for x, I get y equals 15. So 0, 15. And then that's where we see our carrying capacity again. So if there are no mosquitoes at all, the elephants will still have an equilibrium at 15 because that's their carrying capacity. All right. Now let's look at the other null line, y equals 30. Is it possible for y to equal 30 to intersect with y equals 0? No, it isn't. What about y equals 30 to intersect y equals 25x plus 15? I think so. So 30 equals 25x plus 15. 25x equals 15. X equals 15 over 25, so 0.6. So let's assume that X and Y don't stand for individual elephants. Maybe it stands for like hundreds or thousands or something. But what's the equilibrium we get here? So that actually makes sense. X equals 0.6 and Y equals 30. So also under these conditions, we have equilibrium. So we didn't find this equilibrium with our first system, where we didn't have an equilibrium point where both species were present. The only equilibrium points we found were where the foxes were gone. But in the case where you need many, many, many predators to kill a single prey, it looks like that we can have, basically you can have equilibrium where there is still predation happening. So we found all the equilibrium points and all the null lines. So what do these equilibrium points signify in terms of the different species? So I think what this says is for the rabbits and foxes, if there are foxes present, the rabbit population will not be in equilibrium. It just won't be. It'll either be growing or decreasing. Probably going to be cyclical, otherwise there's going to be extinction. But with the elephants and mosquitoes, you can have that. We do have equilibria where, extinction, where they're both elephants and mosquitoes are eradicated. But we also do have an equilibrium where there are 15 elephants, no mosquitoes, and once they're at their carrying capacity, the population will stay stagnant there. But we also have this case where, it looks like the mosquitoes outnumber the elephants by a factor of 50 to 1, and that it will still be equilibrium. What can we say about the stability of these equilibrium points? To try that, let's go ahead and go to Wolfram and get an idea. The elephant and mosquito system in MATLAB here, with an initial condition of 1, and so 120. So 1 for the elephant population, 20 for the mosquito population. So that is an X value a little bit above my equilibrium and a Y value a little bit below. So what happens here? If I run this, so what's happening to the elephant population? So that's X. It looks like, or sorry, X1. Our X variable on the horizontal axis, Y variable on the vertical axis. It looks like at the condition I gave it, we see a, great increase in the predator population. The prey population doesn't seem to be changed by much. At least it looks like it's totally overwhelmed by what's happening with. It looks like dy/dt is much more significant than dx/dt. So let's look at another case. Maybe let's go 0.5 and 20. So now I'm basically to the left and below the equilibrium. And it looks like I see a similar behavior. So again, looks like I would expect the mosquito population to be growing. Actually, I looked to the left and right of this line here. Looks like the mosquito population is dropping to the left of that line and growing to the right of that line. Let's try one more just to be thorough. Let's go 2 and 40. No, 2 and 30. Wait, was 30 the equilibrium point? Yep. So let's go above it, 240. What's going on with these slopes here? Again, so it looks like because of the interaction between the predator and the prey here, in most cases, we're going to see rapid growth of the predator species, especially with respect to the prey. All right, that's all for this question.